Okay, so in the first part, we came up with our continuity equation, and we want to go ahead and continue here through our control volume method. So let's grab our continuity equation, and then we need our constitutive equation, which we know is Fick's first law. Now we're moving in a one dimension in the R direction, so we're just going to change this to a concentration change with respect to R. And now we can substitute that directly in for the flux here. And we have now our equation with the substitution. And so we're going to go ahead and continue on with this. We can pull the D out here as a constant. And we can pull the negative sign out, so those cancel. And so we end up with this form. And then we're going to take this now and apply our steady state condition to it, which is dc dt equals 0. So that comes out. And then, of course, we can multiply by r over d. And so we get rid of that term. And we end up with this form for our governing equation. And so next thing we're going to do is we'll go ahead and integrate. And so the integral of this is then dc dr times r. And this gives us an integration constant. We'll go ahead and move the r's to one side, leave the dc over here, integrate again. So this gives me c. This is the natural log of r. This is a constant, so it comes out. So dr over r is the natural log of r. And then we'll get another integration constant. And so here is our solution then for the concentration profile through as a function of radius as we move from the inner radius Ri to the outer radius Ro. So first thing you can see is we're no longer linear in concentration like we were in the rectangular system, but in fact it goes by the natural log of R. So we will go ahead and apply our boundary conditions. The inner radius, we've got our fixed concentration Ci, and at the outer radius, fixed concentration Co. So we can go ahead and make two equations by substitution. And now we can just go ahead and solve these simultaneously for B1 and B2. And then take those solutions and place them back into this general equation. And if we do that, we're going to end up with this form here. And so there's a little bit of rearrangement that we did. So after we substitute in the solutions here for B1 and B2, we can rearrange this, bring all the concentrations to one side, and we get this nice form here. And so we've got the concentration is a function of the radius r, right? And everything else in here is a constant. So if we wanted to plot this, we're going to need to move CO minus CI back over to this side, and then add this back over to this side, and then we can plot concentration versus position R. But this is a nice handy form to have this solution in, because it gives us a relative fractional value here for concentrations. So our solution concentration here relative to the initial surface divided by the difference in the two surfaces. So we can see again the concentration gradient is not linear any longer. So if we were to go ahead and take and find the flux by Fick's first law, so move this stuff over and then take the derivative dc dr of this equation. Okay, so dc dr of this, if you go ahead and do that, you're going to get this as the solution. And so the first thing we can see right away is that the dc dr term is dependent upon the radius. So as we move out in radius, this term changes. It's no longer a constant like it was in the rectangular system, right? This goes into here. That means our flux is no longer constant. In the rectangular case, the flux was everywhere constant, okay? It's no longer constant. So what is constant in the steady state case? So what is constant if it's not the flux? Okay, again, this is what we got for the flux equation. Depends on position R. If we multiply the flux at any position R by the area, the surface area that it's moving through at that position R, okay, that's 2 pi R times L, then we can see that the R's cancel and everything else is a constant. So the flux times area, in fact, is what is constant. And that should make sense because flux times area is a kilogram per second. So that's actually how much mass is moving per second. And that has to be constant if we're in steady state, otherwise the mass will be changing at any location. We can't have that happen, not in steady state. And so this is really what's constant. And in the rectangular system, this of course was constant as well. It's just in the rectangular system, A that we're moving through, the inner and outer A, were both the same. And so that result then is that the flux was constant. Okay? But in general, it's the flux times the area that has to be constant in all of our systems as long as we're in steady state. We're going to go back and we're going to take a look now at the rate of the helium extraction. Okay, so we're going to use these parameters that we were given in the beginning. And if we use those parameters, one thing we can get is the actual values for the flux as a function of position. Okay, just showing again that it's not constant. So here's the flux value as a function of position as we move from the inner surface at 0.05 to the outer at 0.1 centimeters. Okay, changing flux. And we said flux times area is constant, so if we were to go ahead and look at that one, okay, again, we have a constant. Now the flux times area, if I go ahead and calculate that out, we're going to get 1.8 times 10 to the minus 9 grams per second. If we go ahead and divide that by the density, so grams per liter, we get 1 times 10 to the minus 8 liters per second, or about 10 to the minus 8 meter cubed per hour. That's what we were trying to get to. That's very, very slow. So even though it has 25 times the diffusivity of other gases, including hydrogen, the rate is still very slow. So what can we do to improve that? Well, we could change our tube so that our wall thickness was much, much thinner. Okay, the thinner we can get that wall, the Pyrex, the faster this could go. One way to do that and still have mechanical stability, right? Because if we get this wall too thin, the pressure moving the gas through is just going to cause the walls to collapse. So we do need some mechanical support still. So one way to do that is to make a composite wall in our cylindrical tubes. You can see here a non-woven paper support, microporous support layer, and then we move into the actual wall thickness itself. Okay, this could be one way to really improve the throughput. And in general, this is the way that this process works, but not with helium, but with other systems. And this surface layer, instead of being Pyrex, is some other surface selective layer. The Pyrex case we'll see here is still just too slow. And in fact, you can go ahead and look up on the web the separation of helium from natural gas, and you'll see that it's a completely different process. So this number, if we go ahead and do something like that and really decrease the wall thickness and increase quite a bit the number that we can use, since we're going to decrease the overall size as well of the arrays of tubes, we can go from our -8 number maybe up to something like 10 to the -2 meter cubed per hour. But this is still pretty small in comparison to other separation techniques.